This balcony at the University of Virginia collapsed on graduation day 27 years ago, killing one person and injuring 18 more. The iron rods holding up the balcony had corroded over time and eventually couldn't hold the weight of the graduation crowd. This is just one example of the destructive power of corrosion. Corrosion costs trillions of dollars yearly in the U.S. alone, and pipelines like this one can develop leaks and even explode. Offshore wind turbines break down, metal structures decay, bridges collapse, and ships are slowly eaten away. In order for this type of corrosion to happen, there has to be water and oxygen coming in contact with the metal. Modern ships are mostly made of metals like steel. Corrosion happens on a ship when the metal parts come in contact with the salty water of the ocean. Electrolytes like the salt in the water speed this process up. My name is Parker Flynn and I'm from Charlottesville, Virginia. My project is called Testing Corrosion, Types of Cathodic Protection of Steel. My project explores cathodic protection, a way to protect iron from rust by sending a flow of electrons to keep the iron from becoming a positive ion and reacting with oxygen and hydrogen. But which cathodic protection methods work the best, and why do they work? I got inspired because my uncle, who recently fixed up an old fishing trawler, told me that he uses zinc as a sacrificial metal to protect his boat from corrosion. This is the first type of cathodic protection, attaching a different metal to the iron you are trying to protect. The reactivity series is a chart showing how reactive different metals are. Steel is mostly made of iron, which is a moderately reactive metal. To make the sacrificial metals work, we need to use a metal that is more reactive than iron, like magnesium, zinc, or aluminum. This first method is called galvanic anode cathodic protection. A more modern way to protect ships and pipelines is impressed current cathodic protection, or ICCP, which uses a DC power source such as a battery, solar panel, or generator to send a flow of electrons throughout the iron parts you want to protect. I wanted to know whether ICCP works better than the sacrificial metals. I also wanted to compare what happens when you use different sacrificial metals. I decided to test magnesium and zinc, and then I wanted to see what would happen if I tried to test a less reactive metal, so I chose nickel and copper. My project seeks to prevent the problem of corrosion. What type of cathodic protection will stop corrosion of steel the best? Impressed current cathodic protection, or one of the galvanic anode methods? I hypothesized that magnesium would work the best for cathodic protection of steel because it is higher on the reactivity series. In my project, each piece of sacrificial metal is called an anode because it gives off electrons. For ICCP, I used a piece of graphite as an anode because graphite is unreactive, but it also conducts electricity. The metal I'm trying to protect is called a cathode. I use steel wool as a cathode because it has a lot of surface area. To test the different methods, I set up 6 test containers and filled them with salt water 4 times as salty as the ocean. Each anode was clipped to a container's edge so that it hung down into the salt water. The anode was connected using an electrical wire to the steel wool in the same salt water. In the ICCP's container, the graphite anode was connected to a battery, then the negative end of the battery was wired to the steel wool. The control container had only steel wool and salt water. After 14 days, the steel wool pads were rinsed, pressed, and dried in an oven at 200 degrees Fahrenheit for 3 hours and then weighed. The experiment results supported my hypothesis. The magnesium won by a substantial amount. The second best was the zinc, very closely followed by the nickel, copper, AA battery, and the control, which had no cathodic protection. Despite ICCP's current use in modern ships, performance was only slightly better than the unprotected control, so there should be further investigation into this relatively new technique. As I continue this research, I will use bigger containers for the samples and a solid piece of steel instead of steel wool, so that I can more easily remove rust and measure the change in mass. I will also use chunkier pieces of sacrificial metal, and I will repeat this experiment at least 2 more times with more anodes and try using different types of anti-rust paints on the cathodes. As I mentioned earlier, corrosion can result in devastating and expensive problems. I've talked to several people in this industry, and there's so much more study needed on this topic. If we work together, we can learn about why ICCP works better sometimes than others, and we can find better ways to protect our ships, buildings, bridges, and pipelines, which will increase safety and prosperity for everyone. Thank you.